Units and Dimensional Analysis, lecture number 3. So, to study chemistry, we're going to be talking about converting one thing to another, as we've talked about before. But in order to do that, we're always going to be measuring things, so they're going to have a certain unit. And we're going to have to do conversions between one unit to another to make those things happen. So, in order to be consistent across chemistry, we've developed a set of standard units, the SI units as we call them. SI stands for System International, which is the sort of the French international system that we've adopted. Right? So for a lot of the properties that we're going to be studying, we have some base unit or common unit that we use, standard unit, which we're going to talk about today. But there's also some additional units for other properties that aren't standard or be various, and we're going to talk about how we convert between those different units also today using a thing called dimensional analysis. So let's start talking about our different base units and what they are. Right? The first one that we're going to come in contact and we're going to use a lot is for mass. Right? Mass is something that we're going to measure and talk about quite frequently. And we have to remember that mass is a little different than weight. On Earth they're the same because we've defined them as, well, mass is a constant, it's the amount of material there is. Weight is a variable depending on the local gravitational force dependent on the object. So if we go to the moon, the mass of an object would be the same, but its weight would be vastly different because of the difference in gravitational pull. Right? So when we talk about this, we're going to typically use the term mass because it is the constant one. It's not dependent on gravity. The base unit we've developed for mass is the kilogram, abbreviated kg. We'll talk about the kilo, that prefix, in a little bit and what that means, but that is our base unit. This is the only base unit of these measurements that is based on an actual object. Right? So there's an object, we have a certain dimensions, certain object, and we call that 1 kilogram. It's also the only base unit that has one of these prefixes, and we'll, again, like I said, we'll talk about what these prefixes are in a minute. But the base unit for the SI unit for mass is the kilogram. Most of the time we'll be working in other units, grams, for example. We'll have to convert from this base unit or standard unit. The next property we're going to talk about in base unit is for length. Length is measured, has a base unit of the meter, little m, and it is currently measured by the distance light travels in a vacuum in a certain amount of time. And there, that's the time it takes for light to travel that distance, that fraction of a second. Right? So we're taking, that's measured on this property, the speed of light. The next unit we're going to talk about and work with frequently is time. The base unit for time here is in seconds, and it's currently based on an atomic standard, so we're looking at disintegrations of a compound, that amount of time it takes for those disintegrations to occur is what we're basing this second on. It's far more accurate than the previous measurements we've had, but that's where our current unit of seconds is defined. Next, with temperature, there's a variety of different temperature scale. The base unit or the base scale that we're using is Kelvin, which we signify with a capital K. Notice there's no degrees. Kelvin is an absolute scale, so there is a 0 and all numbers above that. So we don't have negative values for temperature in Kelvin. It's an absolute scale. Where we do in the other two units, Celsius and Fahrenheit. For the conversion to go between those, we're going to show here, the temperature in Kelvin is the temperature in Celsius plus 273.15. That'll give us the temperature in Kelvin compared to degrees Celsius. The conversion between Fahrenheit, which is the sort of the standard American system, versus the rest of the world, degrees Fahrenheit is 9/5 the temperature in Celsius plus 32. Right? So we can do a rearrangement to calculate to go from Celsius to Fahrenheit, if we will. If we have Fahrenheit, we can get Celsius. We'll talk about that and see some examples later. Right? Some other common units or base units that we have don't really use a ton of some of these. Electric current, for example, the base unit is an ampere, capital A. The amount of substance has a base unit, we call that a mole. We'll talk a lot about the mole and its dealings in chemistry starting in chapter 3, but right now we just want you to introduce that is the amount of a substance. luminous intensity has a base units of a candela, which is lowercase cd. Right? So the electric current and the luminous intensity we can talk about. We won't spend a lot of time in this course talking about those, but I want you to be aware that those are the standard units for those values when you come across them. Right? So those are sort of the foundational units that we have. All other units, or most other units, I hate to say all, most other units are what we call a combination unit, or a compound unit. They're a combination of these other base units to get some other unit. Sometimes the combinations are obvious. If we look at volume, for example, when you talk about a volume in meters cubed, right? That's simple to see, but then we'll talk about a liter, and that has a different conversion as well. Or we can talk about density, which is grams per centimeter cubed. That's sort of the base unit for those. But you can see they're compound. They're a combination of more than one of these other units. Sometimes those aren't obvious. We'll talk about an energy unit of a joule, which is a compound unit, but it's not obvious. It doesn't necessarily show where that comes from. And we'll talk more about that later. But all of these units that we talk about, either if they're not the base units that we've talked about today, are a combination of those base units. And we'll get familiar with those as we go through the semester. We talked about the kilograms as having a base unit with a prefix. So let's talk a little bit about what these prefixes are. And what those typically mean is that they are all of the base units that we're working in that has a prefix are based on the metric system or this factor of 10. So if we increase that by a factor of 10, we're going to change the prefix. Right? So it's all equal to this value of 1 here. As you can see, if we have 1, that is equal to 1 times, or 10 to the 0. Right? If we have more, we go by a factor of 10 to 10. That is equal to, in scientific notation, 1 times 10 to the 1. We call that a deca prefix. So deca means 10 of whatever unit comes next. Kilo is 1,000, again, 1 times 10 to the 3rd. Mega is 1,000,000, 1 times 10 to the 6th. If we go smaller than 1, that sort of base unit, to 0.1, that's deci. 0.01, that's centi. 0.001 is milli, lowercase m. Micro is 10 to the minus 6th. Go smaller than that is 10 to the minus 9th. We call that nano. And the smallest one we're showing here that I want you to know is 10 to the minus 12th, which is a pico. So when we do that, we're going to, that 1 picometer, for example, is 1 times 10 to the minus 12th meters. So we're going to set those values the same. So the prefix times the base unit is going to be equal to this number times that base unit. Right? So we can make now a conversion between those using these prefixes. Right? As I said, you need to memorize all of these. These are now fair game. Anytime I see them, you should be able to recognize what those means. Right? Now we're going to introduce this idea of solving problems using a method we call dimensional analysis. So we're going to use and analyze the units. If we can get the units to be the ones we want, then typically we're going to find the correct answer. Right? And it's a standard method of answering problems that I suggest you use all the time. I use all the time. Most of the other professional scientists will use dimensional analysis constantly. So it's a skill that you need to develop. It's one of the first times I'm going to give you a list of things that I suggest you do, that I do when I answer a question. The first thing is to read the question, the entire question. Most of the words we put in the question are important. The ones at the beginning, as well as the ones at the end. You need to read all of them, right? Identify what we're trying to find. Sometimes that's listed first, sometimes it's listed last, sometimes in the middle. Sometimes there's more than one thing we're trying to solve for. You just need to make sure you identify everything we're trying to find in this question. And then we're going to devise a way to go from what we start with, what we know, the information we have, to the information we want. Design a path to get there using conversion factors, and we'll talk about what those are. Set up any necessary calculations. Once we've set this up in sort of a logical way where the units cancel, we're going to actually plug values in there. do the calculation, and then once we have a solution, we're going to look at that solution and ask ourselves, does that solution look correct? Is it reasonable? Is it the right size for what we're expecting? Do the units we get from our calculation equal the units we want? Those types of questions. We want to make sure that those make sense to us there. If not, maybe we should relook at our plan. And then, once we're sort of satisfied with the value we get, read the question again. Is the number we just calculated give us the answer to the question that was asked? Right? So this is sort of the process we want to go through every time we get a question. Yes, it takes time. Sometimes you're going to be writing down information you may not need. But if you do it this way, there's a good chance that you will get the correct answer 90 to 95% of the time, regardless of whether you understand the underlying concepts that are involved. All right? So that's why we're pushing this dimensional analysis. So let's look at an example. So if the diameter of a single carbon atom is 154 picometers, how many atoms would be in a line 100.0 millimeters long, which is about the diameter of a human hair? Right, so we haven't talked about what a carbon atom is. You sort of understand what a diameter is, but the chemistry that's involved here, we don't know anything. But we can still get this answer using this dimensional analysis. As you can see, we're going to go from 100 millimeters to carbon atoms. And the path that we're going to take is underlined here. We're going to go convert from millimeters, which is the length of the line, into meters, and then meters into picometers, and then from picometers into carbon atoms. So this bottom path here is the one that we're going to take. And as you can see at the bottom, this is going to equal that. So we can take the 100 millimeters, which is the length of the hair, times the conversion into meters. So 1 millimeter, which is on the bottom, is equal to 1 times 10 to the minus 3 meters. Since the millimeters are on the top and the bottom of the fraction, they cancel out. Now, we're going to convert from meters to picometers. So 1 picometer is equal to 1 times 10 to the minus 12 meters. Again, making sure that the units that we want end up on the top, units we don't want end up on the bottom, because they will cancel out. And then 1 atom of carbon is equal to 154 picometers. So when we do this calculation, multiply everything that's on the top, divide everything that's on the bottom, and we're left with 6.49 times 10 to the 8th carbon atoms. So whether we understand what that means or not, because we followed the process, we get the correct answer. All right, let's look at one more. What would be the mass of a line if a carbon atom has a mass of 1.993 times 10 to the negative 3 grams? Again, the process we want to go from is mass of an atom to mass of the line. And we can see here we're going to do that in one step. We can take our 6.49 times 10 to the 8th carbon atoms we had before, multiply by this conversion that 1.993 times 10 to the negative 3 grams is 1 carbon atom. Carbon atoms cancel out, and we're left with 1.29 times 10 to the negative 3 grams. Right? So we're going to follow this dimensional analysis where we cancel out units using the idea of fractions to get the units that we want. If we do that correctly using actual conversion factors, right, then we will get the correct answer 90 to 95% of the time, regardless of our understanding of the underlying concepts. Right? Because dimensional analysis is a powerful tool. We'll practice this in class, in the homework. I suggest you sort of adopt this as your sort of standard method for attacking problems. It will help you be successful in this class.
Dad, I done did it.